On this episode of the Embedded Insiders, Brandon and Rich discuss the push and pull of industry hardware standards as support for PCI Express Gen 4 on the latest generation of Intel chipsets has created an inflection point for board and system level specifications that serve both legacy and emerging applications. Next, the Insiders are joined by Mark Doran, president of the UEFI Forum, to discuss Release 2.9 of the firmware OS interface specification. Now that electronic systems of all types support different and advanced memory configurations, will the role of abstraction layers like UEFI become less abstract? Then, a trio of engineers from the Deutsches Elektronen-Synchrotron, or DESY, research center in Hamburg, Germany, wonder how they can balance the demand for performance at some of the most advanced particle accelerators in the world with the need for standards-based computing platforms that protect these sophisticated, publicly funded systems from the cost and availability risks of single-source designs. Assistant Editor Chad Cox reports.
Hello and welcome to Embedded Computing Design's Embedded Insiders. Did you like how I switched that up, Rich?
What was different?
Well,
You didn't introduce me.
I said Rich. I didn't introduce myself.
Right. Let's go. Come on.
I'm Brandon Lewis, Editor-in-Chief of Embedded Computing Design, and this is Rich Nass, EVP and Brand Director, also of Embedded Computing Design.
Thank you. That was better.
And Embedded Computing Design's Embedded Insiders. So I want to talk about standards, which sort of relates to the conversation we had last time when we were talking about, capacitors and operating systems and buck converters and, these fundamental components within an electronic system today. Standards are sort of developed to play a role similar to those that, if we are all using, we all need to send packets over some medium. Okay, why are we all going to create our own? Why don't we just use PCI or PCI Express, Ethernet, etc.? But even beyond that, there are a bunch of embedded hardware standards that we are very familiar with, and that we hope our audience is too. Ones like PICMIGs, COM Express, VITAs, VPX, and VME, so on and so forth. One of the things that's come up recently is with the introduction of PCIe Gen 5, there's always these bleeding edge versions of those interconnects, but the market isn't really ready for them yet. So if you have a standard like a COM Express, like a SMARC, and you want to use PCI Express, should you start building a standard to support those next gen things now? And if you're going to build products based off that standard, are you going to be pushing your PCIe Gen 5 today, or are you going to still be holding back and offering Gen 4 products? So there's this balance, I guess I'm asking. Do you push the market ahead, or do you wait for them to catch up?
Well, that's an easy one. You should always push the market ahead. The reasons are very varied. A simple one, maybe it's not so simple, but one important one is, if you're smart enough to do Gen 5, I should probably, if I'm doing Gen 4, I should probably be looking at your products because you're really smart. And it's definitely a branding issue where you want to be the leader and the expert in that space. That is definitely a reason to make sure that it goes forward. Another important reason to make sure it goes forward is you want to have your stamp on the one that goes forward to make sure that it suits your needs, and thereby your customers' needs, to make sure that your product is at least one of the ones that is used going forward. Even though they're supposed to be built to the same standard, you want to make sure that all the hooks are built in for your customers and for your products, and to be able to move from generation to generation fairly easily.
Yeah, but also you don't want to be the first guy at the party, right? If you're the first guy at the party, you show up and you go, am I early?
Yeah, but as long as the party shows up, that's okay. To be in there waiting for when the party shows up, and it was a weird, whatever the word is that we're using here, but but yeah, being first is okay as long as you're assured that the party is going to follow you. You don't want to be first and have it go in a different direction. But these standards are pretty baked, and it's unlikely it's going to go in a different direction than you expect.
That's true. There are a couple of instances that I'm thinking of in particular where, there's a standard that serves multiple markets, and one of the markets needs really high performance. I'll just go ahead and open the kimono. PICMIG's micro TCA standard was originally developed for telecoms and datacom type applications, but it also serves a whole lot of other use cases in like aerospace and defense and some automation. But one of the really interesting applications is high energy physics to control particle accelerators. So those guys, the data acquisition that's being used on some of these particle accelerators is massive. Obviously, these are the people that are trying to smash photons together and pull out, what all the gunk that comes out of exploding two photons.
I think I learned about that on an episode of Big Bang Theory.
Did you?
Yes.
Can you call up the what's the guy's Chuck Lorre? He wants to be a guest. But of course, that's
what's the market for something like that?
Well, it's very small, but here's the rub is, okay, so obviously the high energy physics guys are like, we need to use the highest bandwidth that we possibly can to capture stuff off our massively megapixel cameras and pump them through the system. Yes, this is very good in theory for the standard, right? It's bleeding edge. It's pushing the standard ahead. At the same time, that's a very small market, to your point. And how many other use cases can you think of that need the bandwidth right now of that type of application? How many other micro TCA use cases need to have a data acquisition system capable of capturing data from many megapixel cameras and shoving it across the backplane instantaneously?
And why would any computer need more than 64 kilobits of memory?
Right.
It just moves on.
Right. Which I think is the point is, look, sooner or later, this is going to be a requirement. Let's just face it.
Of course.
But how far ahead can you get out in front of your customers?
And
right?
How much you're willing to spend to be out ahead in front of your customers.
Right. I mean, because we know that PCIe Gen 5 is coming. That's not up for debate. You just might be waiting for 3 years to sell that.
3 years in computer time is nothing, though.
I don't know if I agree with that. I think 3 years in computer time is a really long time. I mean, that's how many generations of Intel processor is that? 3?
Probably. But in the embedded space, when you're designing for something to have a life of 15 to 20 years, 3 years is not a big deal.
Right, but you still gotta wait for the silicon, right? So
at some point you dive in and you say, okay, this is what's available today. This is leading edge today. This is where it's going to be. It's good enough, and it's going to last me my 15 years.
So do you think that then the answer is to the micro TCA community, bite the bullet and dive in? You're going to need it anyway.
Yep. Easy for me to say. I don't have to make the investment, but yeah.
Right. Exactly.
And they should all be using NAS Lewis operating system.
Yeah, the NLOS.
Now, Mark Doran, president of the UEFI Forum and Intel Fellow, discusses the role and evolution of standardized abstraction layers at the interface of operating systems and platform firmware.
Remind us of what UEFI is, and you mentioned anything that resembles firmware. What does that encompass? What can UEFI be applied to?
Right, sure, yeah. So first, let's expand the acronym out, right? It's easy to get lost in acronym soup. So UEFI stands for Unified Extensible Firmware Interface. And it is, as the name suggests, an interface specification. It's designed to be the way we hold the conversation between firmware that runs on the host CPU and an operating system around the boot transaction. So how do you transfer control from the platform to a running operating system? That's what UEFI interfaces manage for us. The idea is that we have a fairly complete set of abstractions in that interface specification, which should, if we did it right, mean that the operating system folks can use the interface definitions in that book and know nothing else about the platform, at least as far as that transfer of control transaction is concerned. The easiest example, I think, to see why the decoupling helps us is to think back to the time when we transitioned from the old PCAT style keyboards to USB keyboards. It was quite difficult for us to line up support from the firmware and the operating system side to land in the market at the same time. If you want to go buy a machine and be able to use a USB keyboard on it, obviously the machine has to support it, operating system has to support it. And there was sort of this time lag between getting the physical hardware for USB connections into the platform and when we had the operating system support for it deployed out in the marketplace as well. And to mitigate that, what we ended up doing as a community was writing a whole bunch of emulation code that made a brand new shiny USB keyboard look like an old PCAT style one. And I won't bore you with the technical details of how that worked, but suffice it to say, it was being kind, a house of cards, right? It was not the most beautiful piece of engineering ever. It functional eventually. Took a long while to stabilize, but it did get us to the point where the operating system still thought it was dealing with a PCAT keyboard, but in fact it was physical USB hardware. Scroll forward to the UEFI environment, we have an abstraction that describes how to get keystrokes from the firmware. Doesn't say anything about the physical connectivity, doesn't say anything about the device, it just says, here, I'm going to hand you a stream of keystrokes. So now, if at some point we move off USB for some other keyboard connection abstraction, we won't actually have to change the operating system at all. We just drop the new hardware in, build a different driver in the firmware that supports this keystroke stream idea, and yay verily, we've got an intercept in the marketplace. So that kind of decoupling was an important piece of what we were trying to accomplish.
So to be clear, this is the BIOS you're talking about. This is not something that sits on top of the BIOS. Is that correct?
Well, so UEFI is a specification that just talks about interface, and in theory, it doesn't. The specification doesn't say anything about the underlying implementation. When we did the initial development for this, we were working on, and this is back before it was UEFI, we're now talking about that EFI era when it was still an Intel-only specification. We developed it initially for the Itanium processor line. And obviously that was a very different architecture to i32. Since we didn't have any Itanium processor machines initially when we were doing the first development, what we did was cross-develop a course on i32 machines. So building an interface definition that was independent of the underlying firmware and its implementation was sort of an important piece of our development strategy too. So we built it to layer on top of legacy BIOS, but equally then we built it on this, that same interface was designed to support the EFI style implementation that, if you follow the history line, and go look now at tianocore.org for our EDK2 project, the open source property that implements the lion's share of what we use for constructing what as BIOS today. That same implementation, the same interface slots over any number of possible implementations. And people have done other implementations of firmware to support the UEFI interface set along the way as well.
Recently, you introduced launch version 2.9 of the UEFI spec. Obviously, there's some additional support here for newer memory types, new types of hardware, NVDIMMs in particular. But there's also this unaccepted memory type. What is that? And what does that mean exactly?
Isn't that a brilliant name? Tells you there's something interesting in there, but not really what.
Right.
Well, so it turns out that this particular one is all about virtualization and securing virtualization environments. So the idea here is that certain of the processor architectures, certainly Intel and AMD and ARM, have added features to provide more security robustness in virtualization guest environments. And this is where the unaccepted memory type comes in. So one of the more recent things that we've added in those facilities, TDX on the Intel side of things, SEV on the AMD side, is this notion of memory control. And there are now some instructions that are part of those extensions that allow you to say, I am going to accept memory. And by indicating to the processor that you're accepting a region of memory, what it allows the hardware underneath to do is to add additional protections to that memory area so that it can conceal what's in that memory area from even privileged agents like the virtual machine engine itself. So in order to set that up, obviously a virtual machine guest is going to boot an operating system. So it has a little bit of firmware in that guest environment to start the operating system so that we can use we don't need a custom operating system binary to run in the virtualization environment. But that firmware is a little different to the firmware that runs on regular hardware because, hey, we already did full-on memory map discovery when we booted the operating system or the VM that's hosting. So in that case, what we do in that slug of guest firmware is we sort of hand pre-configured memory to the guest environment. So what we do is we mark a certain amount of the memory map that we're handing to that guest environment as unaccepted. And basically what that means is, okay, in the guest environment, here are the regions of memory that you can safely use in your guest for doing things that you want to conceal. You need to say to the underlying physical hardware that you're accepting those memory regions, taking them into your guest environment. And by doing that acceptance maneuver, you're turning on additional protections so that things like the privileged operating system code or the privileged virtual machine code underneath the guest environment can't see into that memory area. So that's what it's for. It's all about setting up the virtual machine guest with a way to say, I want my memory secured from all prying eyes on the platform. UEFI is where we now define the memory map in general that we talk about. That boot conversation part of the biggest thing that we have to tell the operating system is, what does the memory map look like?
Right.
UEFI is like the canonical definition of where the memory map is these days. So it makes sense that when we come up with these new use cases, that's the place where we need to adjust. So it's a very small change in the UEFI spec itself, but it opens up really quite an interesting facility in terms of the capability to deliver.
The conversation to this point has been a lot about how UEFI operates as this abstraction layer, and you don't really want to do much more than that. But if you're serving as a canonical memory map, memory architectures are getting so complex today that could be a definitive source for doing a whole lot of other things further up in the stack, right?
Right, absolutely, yeah. So, we have the memory map definition in the UEFI spec. But if you go look at the ACPI specification, right, the spec that talks about the physical configuration of the machine, that typically it focuses on things that the operating system can't discover algorithmically for itself. So where you have to hand a priori knowledge of the topology of the machine or where physical pieces of equipment are configured, that's something we've grown a lot. So descriptions of these new non-volatile memory technologies and how they fit into the platform. Yes, there's a memory map element, but there's also an element of, so where are these things connected in the machine, right? How do I actually address the controllers that turn these kinds of things on? So we took the ACPI specification under the UEFI Forum's wing. I think it was around about 2009, 2010 kind of time frame. And part of the reason for that is that we need the two to operate together so that you can A, describe the resulting map, but then B, in the configuration side of things, tell the operating system, here are the things you need to know about that physical topology and the layout of the machine so that you can actually turn on the appropriate memory devices, get access to the various regions, and of course understand the different properties, right? DRAM not the same as NVRAM in terms of how it performs. Is memory near? Is it far? All these kinds of things between the memory map and the configuration definitions, we can give the operating system a pretty good set of clues on, okay, here are the toys you have to play with.
It seems like this opens up a whole lot more doors for UEFI to be more than just the interface spec.
Well, I suppose it depends on your perspective. I mean, I like to think of what we do as very much hidden from the general population. All of what we do in the firmware space is kind of, magic behind the scenes. I think we have a clear concept that the UEFI specification itself is just interfaces. We try really hard not to talk about implementation, either in terms of the operating system loaders that are built to read on it or the underlying implementation. But if you look at the way the UEFI spec has evolved over time, we've continued to add interfaces for new services that support all of these new use cases. And we'll continue to do that, right? I mean, it's one of the things that I struggle with getting across to people a little bit. The UEFI spec looks like a very big book. I mean, I think we're north of 2,600 pages now or something. If you print it out, don't print it out, save trees.
Right.
Trust me, it's much better used as a PDF file, but still, it's a big old book. But if you go look at what's actually, it splits into two kinds of elements. There are required elements and then optional elements. And for us, option means if you implement the following, then this is how you must do it, as opposed to you can choose to do it or not, right? Those kinds of options not terribly useful in formal specs. But if you have this facility, then this is how you must express it. That's kind of our option. But if you look at the core of things that are required, it's pretty small. I mean, we have to find interfaces in that set for, go allocate me a blob of memory, because no reasonable program can do very much without being able to do that. Load another image so that we can extend the set of facilities that are in the firmware blob. Those kinds of very basic interfaces are required, but it's a pretty small set. The rest of the book is a collection of optional protocols, protocol being the collective noun we use for a set of interfaces that group around a particular function. It's a set of optional protocols that you can stir in depending on what capabilities and facilities you have in the platform. So you can make very small implementations of what we have, right? The original test case design we had was around a blade system where you had a boot node and then a whole selection of other blades in a chassis kind of frame. And our idea was that the de minimis boot firmware in that case was enough to find the turn on memory and find the network controller, and then pull the rest of the firmware for the rest of the machine across the network and load it as a separate piece. So in that case, we had a few tens of K of firmware built the UEFI way that had a very small footprint in the machine, but leveraged the ability of the fact that there was a reliable backplane in the machine with storage across it that you could fetch more code from. Probably not widely known, but all the iPods in the world, except the little quarter-sized one, they were all EFI machines. So you can build pretty small bootloaders out of EFI technology by right-sizing the choices you make. Or you can build enterprise-class servers with full RAS capabilities, right? I mean, there's a lot of support for that kind of capability in the optional pieces of the UEFI spec as well. So we like to think of it kind of as a Swiss Army knife, right? Particularly when you combine it with the interfaces in the UEFI spec talk about that boot transition. The ACPI spec talks about how the machine is physically put together and some of the power management transactions at runtime. If you combine those two things, we kind of give you a Swiss Army knife of pieces that you can use to build a pretty interesting wide variety of machine designs.
What's next really for UEFI going forward? Where's the work focused now?
There will always be something that the hardware guys will dream up to add into the platform that'll keep us in business for a while, I think. There are some things that obviously I can't talk about that I already know are coming. So I'm not worried about shortage of entertaining problems to go work on. But I guess the other thing I would mention is that we're also, in a sense, starting to change the way we work a little bit. We broadened the governance in standing up the UEFI Forum. In the first place, we sort of broadened out the governance model for the specification to a membership organization. But the folks who are working on system software of all stripes, is even a larger crowd than that. And we've worked on some methods for making it even more accessible, the development process for the specification even more accessible than it is today. So last couple of years, I've introduced this idea of a code first approach to building standards. And we're starting to see some of that work take hold now. So that's kind of a new direction in terms of how we build the standard. So the basic idea there is Historically, for UEFI, what we've done is define the specification, publish it, and then the implementations all run to catch up. The code first approach is more of an open source based idea where we say, okay, let's do development work together in the open source venues that we have. Piano Core EDK2 project is a good example, but not the only one. And we can evolve the code and the specification sort of in parallel in that public venue and get more eyeballs on the problem.
Oh no, Rich, even the standards and specs are going shift left.
That's right. And that's exactly why, right? Is we get more people involved and we get the result done sooner because now we have code and spec in parallel. And what we do is we sort of evolve until the community gathered around it is happy. And then we say, okay, we're going to publish the specification on that basis right at that point. So we can sort of right size the timing of when the specification updates are done and know that we have both better interface definitions because we have working code for them already and get more people involved in the process of helping us build those standards. Again, back to the thought that this is not a space where we see a great deal of feature differentiation, competition kind of work with the general, how do I boot the operating system problem, it being shared, right? We all do better if we collaborate around this technology rather than compete around it. Now, what I'm going to put in the hardware on any given manufacturer platform, these are much more interesting competitive efforts. So we're trying to reduce the amount of energy that people spend on building the firmware because it's not terribly interesting, to be honest. Essential, as we talked about before, right? You can't boot a machine without it. But in and of itself, it's really just grease to get to the operating system from power on. So this idea of trying to democratize and, as you put it, shift left the process a little bit is something that we've been working on too, to sort of evolve the way we build standards.
More information on version 2.9 of the UEFI specification can be found at uefi.org. Next, Assistant Editor Chad Cox enters the highly specialized world of particle accelerators that's being plagued by something commonplace: the need for cutting-edge compute and networking performance in a standard that was designed to support extremely long life cycles.
The DESY Research Center in Hamburg is home to circular accelerators like Petra, and the world's longest linear particle accelerator, the 2.1-mile XFEL. The systems are used in physics experiments that study quantum particles, film chemical reactions, map the structure of viruses like COVID-19, and many others. To say the electronics that support these accelerators are sophisticated is an understatement. For example, 10 times every second, the XFEL generates 2,700 X-ray pulses at a repetition rate of 4.5 megahertz. That means every second the laser emits 27,000 pulses with a luminosity that is multiple orders of magnitude greater than conventional X-rays. Imaging detectors capture 10 gigabytes per second of data from these blasts in support of experiments that measure atomic level wavelengths as infinitesimal as 0.05 nanometers and require femtosecond resolution. The control system that manages XFEL, Caribou, was developed in-house by DESY engineers, but the fast electronics behind Caribou's sensitive timing, measurement, and front-end data acquisition platforms are an open industry standard, MicroTCA 0.4.
XFEL is completely controlled by MicroTCA.
Said Kay Relic, the engineer responsible for standardizing DESY's accelerator control systems around MicroTCA.
There are a lot of other systems involved for slower stuff, but the fast and beam dynamic things, the high precision timing, all this machine protection, all this is done in MicroTCA.
There are more than 35 MicroTCA 0.4 systems distributed along the XFEL's miles-long expanse. Originally designed as a telecom-grade solution, the MicroTCA platforms operate 24/7 for periods of a year or more thanks to integrated reliability features like remote monitoring and control, automatic failure detection, and redundant cooling and power supplies. The MicroTCA chassis accept plug-in cards called Advanced MCs, AMCs, that support a range of modular functionality. At DESY, the AMCs host FPGAs that are used to digitize, synchronize, and process data. Data is then sent over high-speed PCIe and Ethernet interconnects across the backplane and out of the system to control servers and other equipment. For the more specific needs of high-energy physics applications, the 0.4 extension also supports a special clock and trigger topology. In the XFEL timing system, this provides reference frequencies to align sampling rates and deterministically distribute the X-ray laser's pulse pattern information. Rear transition modules, RTMs, which are not present on the micro-TCA base specification, plug into the back of the chassis opposite AMCs to support the additional I/O requirements of physics applications. Despite the system's sophistication, time marches on, and the XFEL was designed and implemented more than 10 years ago. This includes the imaging detectors, which photograph the accelerator's 27,000 X-ray pulses per second.
I think the systems which are driving the most data are the large 2D image detectors, basically X-ray images which are taken.
Says Dr. Patrick Gessler, head of the Electronic and Electrical Engineering Group, who works on the accelerators at the European XFEL.
The different detectors can take between 350 and the one with the most images in one go is 800 images, but they're still producing around 10 gigabytes per second of data, because already now we have the problem that we cannot visualize hundreds of images which are generated with 10 hertz cycles. And now on new technologies, also with the 3D technologies coming into maybe reach, I think they have different kinds of detectors, which we call usually 0D detectors. So these are just ADCs or digitizers. Right now, we have basically digitizer systems going up to 10 giga samples per second. And I think they have some limits right now. But they would like to go even beyond this and also higher vertical resolution on these parts. So this means naturally there will be more and more data generated. And this means we have to cope with this data.
Data isn't being collected in the micro-TCA chassis, just digitized and transmitted to hosting servers where scientists from around the world can analyze it. But micro-TCA is a data pipe in the end-to-end system, one that could potentially burst when DESY installs next-generation detectors that may require terabyte per second transfer speed.
And we are using the CPU in the micro-TCA system to get the data off the cards, to control the cards for sure, but also to get the data off, doing some pre-processing and then sending it off via usually 10G Ethernet, if it's data, otherwise 1G Ethernet, off then into the control system part. And this means the bottleneck right now is the 10G Ethernet as the highest speed we have going out of the crate.
If you want to go to faster communication, that means PCI Express Gen 4 or 5, or even 100 gig Ethernet, you need switches in the crate, and also these switches that controls all the micro-TCA communication, they consume more power than what we can provide now with our 80 watt.
Engineers at the Research Center are considering doubling the total micro-TCA system power consumption to 2 kilowatts. This would not only enable network switching, but also the use of high-performance FPGA and GPU computing solutions that could be used to perform AI. However, this is where things begin to unravel. The first issue is that crosstalk generated by these higher performance compute and connectivity solutions would negatively impact the more sensitive onboard electronics.
So I'm not so sure for the future whether how much really processing and extremely high-speed systems are valuable in the micro-TCA crate if we want to use it also for very sensitive signals at the end. So we have digitizers directly in the crate, which gets directly these low voltage analog sensitive signals to be done. And the risk could be that I think if you combine too much at the end, very, very powerful computation systems with very high speed and a lot of processing with very, very sensitive signals, and this on a very compact chassis, then I think this might end up in maybe compromising the either one or the other side.
Should all of this be in the same system? Going further, is a standard even the right option for this use case? The situation at DESY is one of the few disadvantages of an industry standard, which is the need to reach some level of consensus. Generally speaking, what drives consensus in an industry standard is the market, but whose market? The micro TCA standard serves markets with longer lifecycle requirements like industrial controls, network infrastructure, and testing. The longer deployment cycles mean that fewer sockets are ready to be upgraded in a given period of time, so it takes longer for critical mass to grow around certain technical requirements. As mentioned, Intel's 11th generation processors are the first to support the PCIe Gen 4, which marks 10 years since the introduction of PCIe Gen 3 on Intel Server, the second generation Sandy Bridge, and then the desktop, third generation Ivy Bridge chipsets. Still, it's only a matter of time before all these applications and chipsets advance to current state-of-the-art technologies like PCIe Gen 5 and 100 plus gigabit Ethernet speeds over some type of backplane. If a standard like micro TCA is to continue, something like high-energy physics must drive it to those performance levels. Jan Marjanovic is a senior FPGA developer at the Micro TCA Tech Lab at DESY, a division of the institute that aims to
be kind of as a service provider to other institutes and companies.
While the high-energy physics market is one of the most active micro TCA communities, it is a smaller one in terms of volume of units shipped. That being said, their total investment in particle accelerators, quantum computing instrumentation, atomic fusion and fission equipment, and so on is many billions of dollars, and using a standard like micro TCA helps protect those investments. That is, if a standard like micro TCA can continue supporting their needs.
This was always like a niche product, and I guess it will remain a niche product. An opposite scenario that only DESY would be using micro TCA, right? So in the physics community, then this would not be a standard. This would be like something which is done for DESY. But I mean, now already with having like 20, 30 or so institutes already using, or I don't know the exact number, but I mean, you see when we go to the workshop, there's a lot of people already there. There is at minimum a market which is large enough to sustain at least these niche companies, right? So that's already the first milestone. I think there's going to be this physics community on its own needs a standard, right? So that basically that companies can collaborate and can build this together.
Can accelerators accelerate a standard? Micro TCA technology suppliers like Vadatech, NAT Europe, Samtec, and others are actively involved in the previously mentioned full-channel simulations to determine the viability of more power and higher speed interconnects in micro TCA systems. Of course, running tests and implementing a new business, engineering, and manufacturing strategy are two different things. That's especially true if you're waiting for the market to catch up to the technology. It's even more true when you're dealing with a standard that is designed to support interoperability and, to an extent, backward compatibility. DESY engineers and other members of the physics community understand this and have a vested interest in maintaining it. After all, Relic points out that
all the very different subsystems can use the same standard and ease the development of the software. So if you have a unified standardized system, you can also standardize your software and firmware and this kind of stuff much better than if you have a heterogeneous system.
But how and when to move forward are the questions that must be answered when the standards are mature and the market is confronted with balancing performance and demand.
In worst case, it could be that we make an intermediate step. So we say 4 times 25 gigabit Ethernet, 100 gigabit Ethernet, and PCI Express Gen 4 we can do. Well, we have to then make all the definitions for the in the standard to define these protocols. This can be done, we can work it out, and we want to keep this as a viable standard. So we have to follow what the technology is doing, and the CPUs now these days, Intel CPUs, they provide PCI Express Gen 4. So also Accelerator should be able to do that. Also the FPGAs, they can even go higher already now. So the standard has to follow, I think. It's not the time to make a complete new standard. So when we have optical communication on the backplane, that's a good point of time in my eyes to generate a completely new standard. But this technology is not yet available, so I think we have to keep with the standard as it is and make sure that people do not lose their investment in the technology and all the electronics are bought, and the knowledge, of course, also.
Thanks for listening to this edition of Embedded Insiders. For daily news, videos, and podcasts, visit our website, embeddedcomputing.com.